My name is Ajay. This is Lab 3, Black Hole Activity. So for our intro, the purpose of this lab is to see how forces affect circular motion, specifically gravity in circular motion, and relate mass to the force of gravity, or how it increases the magnitude. So we want to find the mass of a black hole using computational model, as well as find a velocity for an object to overcome gravitational forces. In this case, a spaceship leaving and not crashing into a black hole. So we're going to cover gravity and Newton's second law in this. And the results of the lab are mass as shown on screen, found from part A, and from part B, that is our velocity needed in order to escape the gravity of the black hole without crashing into it. So some concepts we're going to cover. We're going to cover gravitational force, which is determined by this formula below. We're also going to talk about parallel and perpendicular forces. Parallel forces are in the direction of motion and control the magnitude of the velocity for an object, versus perpendicular control the direction. This will become more apparent in our model. Velocity update. Our final velocity is equal to initial velocity plus acceleration times time. This will relate our force to kind of our position and just situation in general. So then Newton's second law, momentum is equal to mass times velocity. We'll use this later when calculating forces. So for part A, our system and surroundings are the star. Our system is a star, surroundings is space and black hole. Only condition that starts with is the only force on the star is the gravity of the black hole. For part B, system is a spacecraft and the surrounding is space, black hole, and planet. Same thing here, only force on the spacecraft is the gravity of both the black hole and the planet. So here's our here's my code for part A, and then at the top we have a we have our email address to kind of differentiate the mass of the star or mass of the black hole from person to person. And then when running this code, this is the solution that we get. And then in this model, the teal arrow represents the parallel force versus parallel momentum versus the magenta is the perpendicular. Part B's code is shown using the mass from part A. We can use that to find the velocity needed to overcome the forces exerted on the spacecraft by the black hole as well as the planet. And then when we run that code, we get the following data and model. And shown underneath the vectorized velocity is the magnitude of the velocity. Discussion, possible sources of error for this is, since this is all computational, we can really, this is a pretty accurate lab, but a computer can only be so precise in terms of constants, so rounding is an issue. It might round in the calculations and not give an exact error or an exact number, just due to iteration and multiple times rounding. So now to the discussion. How is net force and its parallel and perpendicular components, how is that different to the rate of change in momentum and its parallel and perpendicular components? The net force and its parallel and perpendicular components are related to the motion of the object, while the rate is like more toward, or the rate of change for momentum and its parallel and perpendicular components are related to the change in momentum over time. They're related, but they're not exactly the same. And for part 2, how would we find the initial velocity needed to enter an orbit around the black hole? I wasn't able to get this exactly. Spent a good while on it, but the general idea, we would need to reduce the magnitude of the initial velocity for the x direction and increase the velocity in the y direction to kind of put it into the same motion of the planet. But again, I couldn't get actual calculations for it. But that is the end.